bioimaging. My name is Ken Shotman. I'm ABRF's Executive Director. We have a terrific session planned for you today. Thank you for joining us. Before we jump in, I'm going to just make a couple of announcements and housekeeping reminders. Is that okay, Rich?
Yep, absolutely.
All right, hold on. Let me just check my sharing here. All right, great. So again, if you have questions, feel free to put them in the chat. If you'd like to introduce yourselves, we may not be able to see everyone on camera, so you can in the chat put your name, your institution, and where you're joining us from today. If you have suggestions for future programs, either in this series or other ABRF programs, please send us an email, abrf@abrf.org. A couple of updates for ABRF. I hope everyone is familiar with the ABRF's updated strategy. These are our 4 priorities for the next 3 years. You'll probably be contacted by members of our strategy task forces for your input and suggestions on these areas as well. So please feel comfortable to share, and we would appreciate your contributions. And again, this is just another way to look at our strategic goals and objectives for the next 3. All right, upcoming online events. After today, tomorrow, we have our next in our DEIB virtual training series on speaking up. This will be an interactive practice session on bystander intervention and support. Also tomorrow afternoon, we have the ABRF membership orientation. So whether you are a new member, a returning member, or perhaps a long-standing member, and you'd like to learn more about the different ways to get involved in ABRF and the resources available, please join the membership committee for that session tomorrow afternoon. The next session in this series is October 14th on using AI for bioimaging data management. And you can see the link below for more information. It's chapter season. ABRF's chapter calendar is quite full this month and next month. So you can see the locations and dates for each of the chapter meetings coming up for the rest of the year. And if those are convenient to you, the chapter meetings are great ways to connect with colleagues in your region to exchange information, learn more about new technologies, and also meet with local corporate partners to learn more about the products and services that they have available to support your work. We'll just go through these quickly, highlights of each of the chapter meetings. Next week, we'll be in Richmond with a Mad Sci meeting. That'll have a special focus on research in animal-related core facilities, as long with the ABRF Business Skills program on the 15th. Next up is the South Central chapter, our newest chapter. They're pleased to offer their 2nd meeting in Dallas, and you can go to their website to learn more. Following that meeting, we'll be on the West Coast. If I can get that to advance, there we go. We're pleased to move to Seattle. I believe it's the first time in many years that the chapter meeting has been hosted in Seattle at the Fred Hutch Cancer Center. And you can see the QR code there for more information and to register. Followed by the NeuroSkid or Northeastern Regional Chapter meeting in October, hosted at nearby Yale University in New Haven. You'll see some of the interactive sessions that they're planning. And then rounding out the calendar is the Midwest chapter, hosting their meeting in Madison with their ever popular Halloween costume contest. So you still have time to plan your individual or even group costume options for the Midwest meeting. Whether you were able to join us for the ABRF annual meeting this year in Las Vegas or not, all of the recorded content and slides and summaries of the meeting are available to all ABRF members at the link that you see on the screen. You can navigate to this from the homepage of the ABRF website. Of course, with so many sessions going on at the same time, you couldn't attend everything. So this is a way to access some of that valuable content presented at the meeting. I hope you're all contributing and participating in the core community, whether it's on bioimaging or any range of dozens of topics that are available for discussions. You can share resources, you can post documents. If you have any questions about getting signed up with the community, please reach out. And then finally, mark the date for the 2026 annual meeting in Pittsburgh next March. I'm required to mention that it's a schedule shift. We'll be meeting from Saturday through Tuesday, the 28th through the 31st. So please plan to spend your weekend with your colleagues at ABRF next year in Pittsburgh. Registration for that meeting will open probably around the middle of October. And once we finalize all of the program details, which will include the pre-meeting workshops and an expanded version of the successful mini workshops that this group pioneered at this year's meeting, an expanded session within the main program. So stay tuned for and look at the website for more details once that program is finalized. All right, mercifully, that's the end of that. So I'll turn it over to Rich to introduce today's presenters.
Okay, thanks, Ken. So for those of you who don't know me, I'm Rich Cole, basically founder of the LMRG and the current co-chair of it, and I've held other things. I've definitely drank the ABRF Kool-Aid a long time ago. So this series, this is in its second year, the first year really concentrated on AI, both from commercial and from open source codes. And because of the nature of that, we didn't record any of the sessions. Now we're in more of a practical mode here. So like today is on image processing. This is the first part. The second part will be in November. We are going to record them. And basically the recordings will be available on the ABRF website. So given the nature of this, if you miss something or you want to go back to something, you'll be able to actually go back and actually view the slide decks and the presentation. And without any further ado, I'm going to introduce Ben Abrams because he is going to lead off this series. And remember, next month is not going to be the continuation of this. It's going to be data management. Then November, we'll come back to the second part. Take it away, Ben.
All right, can we go to the next slide, please? Okay. There's a little bit of a lag on my side. I'm not sure if that's happening on your side too, but my name is Ben Abrams, and I'm from the University of California at Santa Cruz, where I direct the Life Sciences Microscopy Center.
There is a lag. It's not just you.
Okay.
There we go.
Okay, so I'm joined by Dina and David here, who I guess will introduce themselves at the start of their sections. And we're just going to start off here with a question to the audience, and that is, just looking at this image, what do you think? Can you analyze this image? And we'll present a Slido on the next slide so you can answer that question.
Use your phone to QR code and vote.
Yeah.
That. Anybody else? Okay, the votes are coming in.
All right.
It looks like about half the people have voted, so I'm going to share this. You guys can keep voting. This gets updated in real time. So, looks like, Ben, can you read that?
Yeah. Looks like we have 36%, 45%, I can't tell, 36% yes, and 18% no. So it looks like we have 11 responses so far. There's 21 people here. Maybe give it another 10 or 15 seconds. I don't know.
I don't think it's changing.
Okay, great. Thank you. All right, so I guess we can go on to the next slide then. All right, so I think that most people in this audience are aware that microscopy can be used in a variety of applications, and it's really powerful for a lot of different ways that people can observe samples and understand their sample. It can be used very powerfully both as an exploratory tool to come up with a hypothesis or to spark interest just from pure observation. You can use it for screens, and it gets a lot of its power because it's a multimodal instrument. You know, you can look at your data in a lot of different dimensions, time, space, with molecular specificity, and you can get quite a lot out of your images. Next slide, please. But we also know that microscopy is a really valuable tool for hypothesis-driven quantitative analysis. And these are just some extractions or segmentations and extraction data on the left here, and then a plot of some data that was generated in a microscopy experiment on the right. Examples of that. Next slide, please. So, really, regardless of your intent, a couple of things that those practicing imaging and imaging science must really master are knowing the limits of what kind of information can be extracted from an image and what kind of information is reliable, and how do you know if that information is reliable. And then you also need to know how to extract it. Next slide, please. Okay, please play okay, great. That's you see that little macro is going where someone has gone in and this is actually an example macro that I wrote just to extract information. And the thing is that as we'll see in a moment, modern digital images are inherently data maps. So yes, you can extract quantitative information from almost any image, but until and unless you have a important question or a well-formulated hypothesis in mind to test it, you don't know whether the information that you're trying to extract from your image or that you're extracting from your image is really relevant. And if you don't know how the image is collected and what the reliable or the important parameters are in your image collection, you won't know how reliable those quantitative measures are. Next slide, please. So when I present this, or I often talk about this, I really love to refer to this this figure 1 from one of my favorite microscopy publications that came from Tian-Liang Chu's group at Genelia. And you can see there's a QR code to this paper. I would definitely encourage anybody that hasn't already read this paper to check it out. It's a fantastic resource. And I really like this figure because it serves as a roadmap to design or critically design a microscopy experiment. And what this paper does, or this opinion piece does, is it talks about the kind of the traditional way that a imaging experiment may be conducted with a hypothesis, planning, sample preparation, and so on until you get a result. But what these authors do is they really encourage you to slow down and think about and pause at the experimental planning stage and really kind of reverse engineer your plan to imagine, after you've formulated your hypothesis, what would you have, or what would informative results look like? What kind of data would you need to have those informative results? That goes on to determine or define the parameters that you're going to use or that you're going to need, and the capabilities, the instrument that you're going to need to select. And then this also brings up the important point that all of this is a iterative process. So you go through this thinking scheme of thinking about the results and determining what scope you're going to use, and then you want to get to a experimental output, which then you can test and find out whether it really is informative in the way that you imagine it is, and you are planning for it to be. And if not, you go through the cycle again. And so, to me, this is a great way to do hypothesis-driven science, and in a way that's efficient, because you're planning what to do. You don't have to waste a lot of time exploring and taking more data than you need to. But I also know, as a core director, that a lot of times people will come into my office and bring me an image and say, hey, can I analyze this? Or how can I analyze this? And so I find that this figure is also a really nice framework for thinking critically about data that you already have. Well, once you have this, what kind of scope did you use? How did you set up that scope? What were the parameters that you set up to collect your data? And so it's really informative as a guide to think critically about your data also. So this is obviously not a journal club on this particular paper, so we can move on, but I would encourage everyone to read this publication. Next slide, please. Okay, so what we're really going to focus on today is knowing the limits of what information can be extracted from the image. How do you know what is reliable information in your image, and how that image can inform your analysis. And then the next sessions or the next session will be more focused on how to extract that information. Okay, next slide, please. Okay, so we're going to dive right into it. And so, as I mentioned a little bit earlier on, a modern digital image is inherently a data map. And if you were to zoom into your image with the interpolation turned off, you will see individual pixels, and every one of these pixels is going to have a particular numeric value assigned to it. And generally, higher numeric values are going to correspond to higher intensity and suggest the higher abundance of a particular target in your image. And you can just see the matrix here on the right aligns with the value or the image on the left, where you have lower values in darker areas and higher values in more bright areas. Next slide, please. It's also really interesting to consider that even this 2D plot is in some ways a graph of your intensities. And if you can play the animation here, you can see if you turn it on its side, the initial view was an XY view of this 2D image. But if you flip it on the side, you can see that the intensity values here can also be graphed. It looks like this is an 8-bit image. We'll get more into bit depth in a little bit. But this is also another way to conceptualize the image that you're getting off your microscope. Next slide, please. Okay, so I mentioned earlier that there's microscopy is really valuable because it can you can probe a lot of things. You can probe your sample in a lot of different dimensions. This is a description of many of those dimensions. So if you start off with a 0 dimension, it's just like that image that I showed you on the slide before last, where you just have numerical values. And if you were to plot a line down one row of that table that I showed you with the numerical values, you get the one-dimensional data where you have the intensity value over like the x coordinate. Okay. Then if you look in the two-dimensional image, you have both X and Y. If you want to add colors to that, indicating different molecular identities, you can get to a third dimension. You can add the Z spatial dimension to get to a 4-dimensional data set. And then you can also look at 4 dimensions over time for a 5-dimensional data set. Next slide, please. This is an example, a couple examples of a presentation or presentations of how 5-dimensional data sets may be visualized. And if you can play the top movie. The top movie is showing a maximum intensity projection of a 3D movie over time, where you're looking at mitosis in the sample. And down below, what we're seeing is that same representation, but now instead of all those Z positions being collapsed into one 2D representation, you can see them actually being shown in their actual focal plane where they are captured. And that's just an example of a multidimensional data set. Okay, next slide, please.
I think I jump in now. So I wanted to talk a little bit more about when you're looking at your image and you're looking at these pixels, what is a histogram and what is bit depth, and how does that impact image quality? So on the left, we have an image. You guys are familiar with images like this. It's just a cytoskeleton of a cell. If you were actually to run your mouse over the cursor, you would see that there's an intensity value at each of those pixels, as you saw earlier in Ben's presentation. If you were to take those values, you could plot them along the histogram, where the y-axis is telling you the total number of pixels, and the x-axis is telling you the intensity levels themselves. So with most fluorescence images, you have a histogram that looks like this, where the left side of the histogram are those black background level pixels. They don't have that much data that you tend to be interested in. The data you care most about tends to be on the right-hand side of the image, and that is where your structures lie, right? So over in here, it's associated with the cytoskeletal structures. Okay, so the scale at which this maxes out at is based on bit depth. So bit depth, when we're talking about an 8-bit or a 2-bit or whatever bit image, is the number of shades of gray in a display, in an image itself. And it's expressed as 2 to the nth factor. So a 2-bit image is 2 to the 2nd power, which is 4 shades of gray. Black and white count as a value. So it's black, white, 2 shades of gray. 4-bit image, 16 shades. 8-bit image, and this is what your phone's taking. This is what most of the images you see in the world are taking, is 256 shades. What does this look like? Well, I think we can all agree that this is a picture of a leaf. This is a 1-bit image. It actually only has black and white pixels on it. And you can see there's some droplets on here, and there's a little seam running across the middle of the leaf, but it's kind of hard to get information out of it. So 2-bit images, black, white, 2 shades of gray. I'm starting to see a little more detail. 8-bit, if you're as old as I am, when you first had Macs back in the day, they had, actually, I'm sorry, the 4-bit one's gone. So 8-bit is what your phone is taking. 16 shades or 256 shades of gray are in there. This is what your eye is capable of detecting. But scientific data is usually more than that. And why is that? When we look at a histogram, if you were to take that 1-bit image and you look at the histogram, you would see that all of your pixels fall into 2 buckets. They're either 0 or 1, right? If you want to look at a 5% change in intensity value, that's going to be really difficult to see on something like this. 4-bit images, now I've got 4 buckets. 8-bit, now I've got 256. Okay, 12-bit. This is what like the Nikon point scanning confocals are using. A lot of point scanners use 12-bit image. You now go from 256 shades of gray all the way out to 4096. So it allows you to see finer and finer details, just as we can here, right? So these droplets become easier to tell. Right? And most cameras actually run all the way out into 16-bit mode, and there you have 65,000 different values to bin your data into. All right. A little note about 16-bit images. Your eye doesn't see the difference, and neither does the display. And we're going to talk about displaying your data a little bit later on in this presentation. So how does bit depth impact image size? Well, it makes a difference. So if you have an image that's 512 by 512, that's around 257 KB. If you now have that in 16-bit mode, you double the size, right? If you now add more pixels to it, or if you save that as a JPEG, which we'll talk about later on, and that becomes a 3-channel image, your image size goes up. So you can easily take an image here and turn it into this image here and suddenly increase your data significantly, your data size. Okay. So most of us, when we're sitting at the microscope, aren't just looking at a single channel image. We're usually looking at a 3-dimensional data set. And what I mean by 3D, I mean 3 channels or several channels. So I have this picture of the cells. These are HeLa cells. How does a fluorescent microscope do this? It doesn't take an RGB image using an RGB camera. It takes a monochrome image. In most cases, scientific images do this, monochrome images sequentially, and combines them into one image after the fact. Now, this is really important because what it means is your capture is going to be monochromatic, and we are just pseudo-coloring this after the fact. Now you're going to say to me, Dina, that's not how my phone works, and I've taken lots of H&E images, and I'm not taking those channels sequentially, and you're absolutely right. You're using our RGB camera. That's a little bit different. The most simplest of these cameras have filters glued on individual pixels. Then you've got a green pixel, a red pixel, a blue pixel. Those are binned together, and you get your final image. The reason we don't do this for scientific imaging, for fluorescent imaging, is A, it doesn't have the sensitivity of most fluorescent cameras. You're limited in what filters you can choose, right? So when you're light limited, you don't go this route, even if you have an RGB camera on your microscope. For other modes, you use the monochromatic capture. All right. Speaking of coloring, when we're capturing in monochrome, you can pseudo color your images whatever you want. And this can really impact your perception of what your data is. So Ben generated this slide. I think it illustrates the point perfectly. So upper left-hand corner, our eyes are great at seeing greens, right? This is what we've evolved to do. We're magnificent in it. So anything that's in the green channel or close to green is really going to pop, right? Things that are lighter in color are going to pop. Things that are blue, things that are red are not going to be as easy to discern by eye. If you go to journals nowadays, they will oftentimes ask you to not use red and green in your images because colorblind people can no longer see it. So even though these structures are equally present in all four of these images, you can see how the lysosomes look completely different in panel 4 as opposed to panel 2. And that's all just based on color. You can use this to your advantage when you are pseudo-coloring your images, when you want to highlight structures. All right. Speaking of displays, our monitors are never 16-bit. The most expensive ones out there will give you a 10-bit depth display. So oftentimes you're going to be adjusting your image when you're visualizing it on your computer screen. And the two filters everybody tends to play with are brightness and contrast. Okay? These filters have a linear change. They are applying a mathematical formula to every single pixel in your data, and that is linear. So we're going to go back to these lysosomes. We're going to look at the original image. We're going to take this and we're going to adjust the brightness and contrast. So when we adjust brightness, what we're saying is if I've got an input value, can you guys see the arrow on your screen? Yes. Okay, when you've got an input value, instead of it being, let's say this was, input was 5, output was 5 on the original, the output is now going to be 20, right? So you're taking those values and you're scaling them up. You are taking the brightest pixels, and in this case, I'm making them look like they're saturated. So on the image on the left, let's say this brightest pixel was maxed out at 255. I'm going to say, no, make anything that looks greater than 155 look like it's 255. And that is why this looks like it's saturating over here. All right. Contrast is shearing off the bottom, if you will, of that. So anything that has an intensity value of, I don't know, 50, make it look like it's 0. And when you adjust them together, you get images that look like the image on the right. Now, when it comes to publishing, when it comes to highlighting these in your figures, what is acceptable? In general, journals may be changing. In the past, you did not have to disclose brightness and contrast adjustments to your images as long as you're adjusting everything in the same manner. If you are going to change your brightness and contrast, you need to do it equivalently to the same exact values across everything in your panel. If I had this sample down on the microscope, I actually could generate an image like panel A right here, this brightness one, just by turning up the exposure time or turning up the laser power or turning up the dwell time. I could increase the contrast by playing with the offset, which you never want to do. But these are images that correspond to what's happening in the biology. So you would be able to generate them in your image, right? This is important because there's another filter that people sometimes play with that you need to disclose every single time when you're publishing, and that is the gamma correction. So I've got the image on the left, right? The original one. I've got these lysosomes and I've got this background expression here. I don't know what that is. Could be non-specific dye. It could actually be a structure I care about. When you adjust gamma, what you're doing is you're doing a non-linear change. So just to remind you, if I adjust the brightness, what happens is these structures start blowing out in order to get this. When I adjust gamma, I'm saying keep the bright stuff at a certain level and bring the dim stuff up to match it. So this is very, very useful when you have something like I have a high concentration of protein in my nucleus, but there's also structures in my cytoplasm that I care about, and I want to be able to highlight those without making my nucleus look like the sun. So instead of adjusting the brightness, which is going to blow out the nucleus, I'm going to adjust gamma to highlight the structures that have lower protein expression. Now, it's acceptable to do something like this, but you have to disclose it because this no longer matches what you see at the microscope, right? The protein levels in these structures over here do not match what is actually happening when I turn up the exposure, right? And conversely, the same thing with gamma. So when it increases, so I'm dampening down the dim stuff at a different rate. All right. We've got a comment. So to me, gamma change is fine for illustration, of course, reporting it, but it should not be applied to the underlying data. Great point, okay, that's absolutely correct. These adjustments are for display purposes only. You also can use them when you are segmenting things, right? But you never apply and override the values that you've got in your original images. So we keep those. Any other comments I should highlight it? Okay, we're gonna move on to the next slide. And we're happy to discuss. We can take questions mid-presentation. We can take them at the end too. All right, saturation. So this is something I've mentioned in the past. I just want to highlight what it is again. So if you think of your pixel as a bucket, you have photons coming into the bucket and they're filling up, right? And they read out once they hit a certain level, right? So if it's just water in a bucket, this has an intensity level of 0. This has an intensity level, let's say, of 100. This has an intensity level of 255, and it's maxed out. We never really want to max out our pixels because what winds up happening is you have no idea, once you've maxed out the detector, how much light is actually hitting that pixel. So here are 3 different pixels. You can see that the number of photons that are hitting them are very, very different, but the readout in these 3 cases is going to be exactly the same. So when you're doing analysis, that is something like spectral unmixing, deconvolution, where the intensity really matters, this is going to be absolute catastrophe for you. So avoid saturation. The other thing we want to point out is you want to have detectors that have good dynamic range. And when you have detectors that have good dynamic range, you don't want to destroy yourself, right? So on the left, we have a picture that is over and undersaturated, right? And you can see the oversaturation over here in the background. We've lost the ability to see the clouds. Now, when you set the detector such that your background is really, really black, it's at 0 all the way around, you will lose some information. You can see the ceiling over here is gone. Newer systems tend to lock you out of your offset slider, but we still see this coming into the facility where people are sliding around the offset to get rid of the background. Background's important. So ideally when you're imaging, you want not 0, you want 1 to 252 on an 8-bit detector. And I will say the disclaimer is the newer Olympus systems, the FlowView 4000s, have a newfangled detector where 0 really is kind of 0 and there's not much you can do about it. And that's fine. The detectors are set up to have an enormous dynamic range. Okay, we have another vote here. This is another Slido. So we're going to have you vote on your favorite image. So we've got A, B, C, and D. And when you guys get a chance, open up your phones and start voting away at which one you like best. So you're sitting at the microscope and you're trying to capture an image. And how are you going to set up your detectors? We've got 3, 5, 6, 7. Okay. Anybody else want to vote? We've got 8. Let's see if we can get 1 or 2 more in there. Okay. All right, I'm gonna go ahead and share this. All right, so we've got an overwhelming vote for 12, for D, which goes to show you, we have a lot of people here who have a ton of microscopy experience, because natural instinct, right? Most people are drawn to image B. Humans love high contrast images. We like images that pop. We like images that shine. We like images that saturate, unless it's been beaten out of you at the microscope by, your professor or your analysis pipelines. So yes, the answer is in fact D, but you wouldn't actually know it by looking at the image in many cases. What you really need to do is look at the histograms. So when you image, the histogram is king, right? When we're looking at A, B, C, and D, we always love histograms that look like this, where they take advantage of the full range of the detector. They're going out near the end of this, but they're not saturating. And I can see saturation here because, oops, I have maxed out my detector. And saturation is really, really, really bad. And you can see that in this image right here. In B, I've saturated my detector, and when I zoom in on those little pollen spores, I can tell that I've saturated it in this area, and it now looks solid as opposed to whole. And no matter what I do, I can't get that back because the detector is maxed out in those pixels. So saturation, even if you are just quantifying, how many spots do I have here and how big are they and are they hollow, can really mess up your data. So another reason not to saturate. Okay, I am going to pass this over now to David, who's going to talk a little bit about signal to noise.
So the vote just tells us that a lot of people knows what they're doing in here because they're whatever leading facilities and trying to convince people. So the talk is about, but we put it together to see examples how to explain things that we struggled with when we explained them to users. One thing the people have a hard time to wrap their brain around is signal to noise. So when I ask people, when I show him this curve, what is the signal to noise of this, I get several answers, something like, it's 10 because this is where the background is, but I trick them because the signal to noise of this curve is infinity. There is no noise. But when I get asked from Nikon or other people say you need a signal to noise of 6 to do certain things, people say, what does that mean? So I wrote a little a program in there that I start is with signal to noise that's really bad, and then I increase the signal to noise. You know what's in there. There are two hills, and you can get an idea at what signal to noise you say, okay, now I can identify two hills, now I can fit the vertex of them and what the point is. So when you play this, you see that when you have a signal to noise of 1 and 2, it's crap, you can't tell nothing. But when you have a signal to noise of 3 and 4, you can see two hills. At 6, you can say, okay, I can start to fit stuff. And something like 8, this is where the storm range is to get positions. After 8 and 10, you never get to the microscopy, but these values are still there. So technically, you're aiming for a signal to noise of 6. And just to make it clear again and again for users is that the signal to noise is the signal is the moving of up and down, and the noise is the jiggering around this. So it's not the height of the background, not what it is. It's a relationship between your noise in the image and the height. How much height is the height compared to the width of the noise? And when you go to images and then you will adjust the brightness and contrast, you will see exactly this. It's not depending on how many photons and how many values you have. It's depending on how you are sticking out of the noise. I literally don't care if you have 4,000, 5,000 or 10,000 count. I care that the noise is low compared to the signal. So what you see here, when you have a signal to noise of 23, it's clear like hell. When you have a signal to noise around 2 and lower, it's hard to do anything. It will be hard to do anything even in image analyzing. This leads us to the fact is we have to spend a little bit of time to get an idea where the noise is coming from. In our digital systems, noise is omniscient. It's everywhere there. It's part of how we design our cameras and our detectors. That means is even when I have a camera that is totally closed, it's dark noise, you think, yeah, when it's dark, it's 0. But then when you adjust the brightness and contrast, you will see, no, it looks like a sea of jumping pixels up and down. So this is the dark noise of this. For example, the dark noise is mostly triggered by thermal fluctuations. That's the reason all the detectors are cooled down, because this will lower down the dark noise of the camera, and that's the reason you have cameras like -80 and -40, because they just say, okay, that's a simple trick to keep the dark noise down. Okay, so but nowadays people say, I don't care about the noise anymore because I have these beautiful boxes with the new AI stuff that can convert, that can make me in a magic box signal to noise better. So we just took 2 images from our Nikon scopes and used denoise AI to denoise them. But what this leads to is that when the signal to noise from the beginning is bad, the outcome is bad. So you can't rely on that you have a magic box that can generate signal to noise or make it better. You need a certain input with a certain signal to noise, so 6, 7, whatever, to make it even better for yourself. And the next thing that would be, it's very bad, is because this will change the histograms of this. So when you are relying on comparing intensity to each other, forget it. There are very strong non-linear functions in here. When you apply the denoising, it's good for segmentation, but for comparison intensities in the denoised image, forget it. So there's no way to do this. So the other concept I want to talk about is resolution. Oftentimes, resolution is it's coming from the NA of the objective and only from the NA of the objective. There's one factor in there that is the wavelength. So meaning when you have shorter wavelengths, you get better resolution. When you have longer wavelengths, you have a worse resolution. But the wavelengths ranging from 480 to 900, the changes in wavelengths is not so critical. The NA is a way bigger factor. And then there's a 4 factor in there where we come to a second why this is there and what is doing this. But in general, you can say on a wide field scope, we have 0.6 multiplied by the wavelengths divided by the NA gives you the resolution to distinguish 2 spots that come together. Yeah, next slide. So I just make a small little animation that you get an idea. So these are 2 Gaussian functions. Normally you have to do array-disk, but I'm lazy. We do all this stuff. And then we move them together. And what you see is when they are 2 sigma away, they fuse together. So this is exactly the resolution limit in the microscope. Then you have 2 points. They are defined the size of this by the NA of the objective. And this defines in how close they come together until they blur together. This drove me nuts when I first did this because you look in the internet and in the formula, and then the 4 factor is changing. And then why the heck is changing? Because different people invented that for their application. So in this case, we have 3, the relay, the sparrows, and the Abbe. The 4 factors only define how deep the valley is in between the spots. So when you have Abbe, there's a small valley. When you have Raylight, it's a big one. When you have Sparrow, there's none. When you think about signal to noise now is, now the signal to noise defines as well how good your resolution is, because when your noise is big, you don't know if the noise is a valley or the noise is just a dip. Right, so what you need is a nice NA and a nice signal to noise to be able to use the highest resolution from your objective. Okay, so this is just an example that you understand that we are diffraction limited on our normal microscope. That's the reason the people got the Nobel Prize in 2006, because they said, okay, that's not true anymore. But until then, everybody knows this formula and say, okay, I have a diffraction limited system that depending on the opening angle of the objective, and you can type this in, and the maximum opening angle is 180 degrees. This is a zenith of 1.5 something, and then that's the maximum you can do with a normal microscope. Without any additional hardware, this was the maximum we can do with a normal optical microscope. Oh, how far did I go? Okay. There's a concept of that the optical resolution is defined by the objective, but at the same time now you have digital detectors that have a pixel size in there. And they are both working, and you need to find the sweet spot with each other. Meaning, when you're going from right to left, you increase your optical resolution. When you're going from down to up, you make the pixel size smaller. And there's always a sweet spot where both meet the criteria. So it makes no sense to have a very good optical, very bad optical resolution and small pixel size, because you will only get more information without really resolution. And on the opposite side, when you have a very good optical resolution and you choose a very chunky pixel size, you're not benefiting from this. So in theory, you have a good optical resolution, but because your pixel size is so big, you will see nothing. So there's a relationship between pixel size and resolution, and the relationship was defined by, next slides. Okay. One more, sorry. One more. This is just an example when you use a good NA, a good resolution objective versus a bad resolution objective. So in one case, you can see small structures, and the other case, they will just blur together. So this is just an example that the only number we as a microscopy wants to know is the NA and not the magnification most of the time, because it's useless, right? So we like the NA because then we can just, okay, this is the grade of objective you use for this. Okay, so there's a relationship between the resolution and the pixel size, and this comes from Nyquist Shannon. They said that when you have a frequency from a signal that goes up and down, half of them should be the pixel size, half of sigma. In this case, for an example, on the left-hand side, you see the signal, and on the right-hand side, you see what it will look like when you have different pixel size to represent what you see on the left-hand side. And it's easy to understand. When you use B and C, you don't reflect the curves. What you want is D. So you need to adjust the pixel size to your optical resolution. Normally you do this by the optical resolution is the full width half maximum. From the full width half maximum to the standard deviation, it's 2.33 sigma. So meaning you divide the stuff, and then you can calculate the pixel size you need for this. Luckily, most of the time, we don't do this on our confocals because there is a Nyquist button or an optimum button. So technically, you can go in and type the numbers into a calculator and see what your pixel size is, but normally you don't. Normally you say Nyquist, and then you go with Nyquist and you do this. That's a little bit the opposite when you don't have a point scanner. When you go to the next slide, is because there the detector is fixed. And it's even worse because the fixed distance on the detector is multiplied by the magnification of your objective. Meaning, when you have a 100x objective, this length is literally 100 times smaller. So you can calculate the pixel size. But this is the example if when you have a certain NA with a certain wavelength, what pixel size you want to have on your camera that your spinning disk is meeting the Nyquist criteria with this. So you have two things you can change now is you can buy a camera with a certain pitch size, and you can change the tube length in front of the camera to set the pixels in there. But this chart is there that you understand is even when you have a physical device like a camera, you are able to optimize this for the objective, for the optical pinholes with the wavelengths that you meet this criteria. And I guess that's it, right?
Nothing more.
Okay. This is the example just to visualize what you will get is on the left-hand side, you see when your pixels are too big, and then you lose the structure you want to resolve. In the middle, you see where the pixel size fits exactly the optical resolution. You get a nice line, you can segment and trace. And on the right-hand side, you see when you choose a pixel size that is 2 times too small. Technically, you have the resolution in there, but there's an empty resolution, and you will increase the noise on this, right? So the take-home message is try to encourage everybody to use Nyquist as close as possible to your optical resolution. And I guess now, Ben, it's you.
Okay. All right, so this is a fun cartoon. People looking through different optics and imagining the same thing here. Let's move on to the next slide. So we just discussed several really important factors that communicate the quality of your image. And it's really important that all these details are recorded. And this is typically done in the metadata file. And so this is an example of a metadata file. I think this is a Zeiss CZI file. And it just the metadata files are going to record all the hardware and software settings that were in place when you captured the image. For example, the logical size, the spatial dimensions of your overall image, your pixel size, usually the objective that you use, including the NA, the wavelengths that were used to capture, your filter specifications, the camera that you used, how you were operating it, whether you were using binning, things like obvious things like exposure time too. So this is one presentation of the metadata. Next slide, please. And fortunately for us, we can also view this metadata in Fiji. I think everyone here knows that Fiji is just a build of ImageJ that's got a whole lot of additional functionality built into it. And when you open your images in Fiji, you have the option to view the metadata in 2 different ways. You can view the open microscopy environment metadata, which is presented here, which is, I find it to be less information, but a little bit easier to read in some ways and pick out specific details that you want to see, like the pixel sizes and things like that. Next slide, please. But you can also view the original metadata, which has a ton of information of it, several screens worth. And you can resize your columns. Sometimes when you first open the original metadata, the words will look jumbled because they look like they're on top of each other, but you can resize the columns to make sure that they don't overlap. And the nice thing about the original metadata, it is way more information, but it's also searchable. So if you look into it, you can type in your favorite parameter and it will pull that up. And then the trick is to figure out how the parameters that you care about are actually encoded in the metadata. And that's, but you can do that. And it's not that difficult to figure out. Okay, next slide. Okay, so there are all the major microscopy company software packages will have their own kind of proprietary format. I think Nikon uses this ND2, Leica uses the .lif, Zeiss is currently using the CZI. I think that Olympus is currently using .oir and VS2 or SV2 or something like that. I'm not sure. I don't use Olympus scopes myself, but they're all going to have the metadata baked in to the image file. And so when I'm training new users, I'm always recommending that people always keep a copy of their file in that original format just to preserve that metadata, because it really is valuable to you in enhancing the rigor and reproducibility of your work, and also just going back to that image you took 3 months ago and knowing, oh, did I take this in a way that's going to allow me to analyze the image in the way that I really want to? Is it going to be reliable? Okay. So another common way to save image data is in this open microscopy environment TIFF. This is another lossless format that also has some metadata associated with it. There's an H5 file that is used for really large data sets. Regular TIFFs, which can be abbreviated with 2 Fs or 1 F, are essentially the same as in their ability to be lossless, but they usually have, or almost always have, less metadata than the OME or the original proprietary format. There's also bitmaps and GIFs and PNGs. These are also lossless. I think I often suggest these as options for, quick, throw it in your PowerPoint and get it onto your presentation in an hour. So these are compressible, and they don't have metadata, and recognize or realize that when you are saving any of your data in these formats, it usually it becomes like an RGB format, but it also has a lower bit depth. So you are downsampling your data whenever you're using those formats. And then last here we have the JPEG, which is lossy and compresses your image, and the quality degrades over time. And we have an illustration of how that happens in the next slide. And you can see that if you have your original file that shows up in these nice brilliant colors with a nice spatial resolution, if you do multiple encodings, you'll degrade the quality of your data over time. And so you really want to avoid introducing these kind of artifacts in your analysis by choosing the wrong format. Okay, next slide, please. Okay, so another thing that you have to be aware of are other artifacts that can be present in your image. These can be based on how you captured the image, or how you operated your instrument, whether it be a camera or another instrument. For example, this camera artifact with this fan is showing a dynamic event that was captured with too low of a frame rate. So on the left-hand panel here, you're seeing the blade is blurring because you're not capturing a high enough speed, essentially. Next illustration. Okay, what this is showing on the left here, or sorry, now on the right-hand side of your screen is an image captured using like a CCD array or just a standard camera. The left-hand picture here was captured properly, but the right-hand picture this is showing this effect called blooming, and that's essentially where there's too much charge that is getting built up on a certain part of your array or your sensor. Usually, this can be thought of as a similar phenomenon to saturation, but it's actually a accumulation of charge that's building up in the sensor and kind of spilling over and causing this effect. And it can also it can be affecting maybe just half of your sensor, depending on how you're operating your shutter. Next component. You can also have artifacts that may result from using a low quality of objective, or having an optic that's got something on it where it's blocking out part of the light. Here we're seeing different wavelengths of light being focused to different places on the image. The green here is rapidly or greatly displaced from the red signal on the left, but then afterwards you can see that it's been corrected on the right-hand panel so that they align as they should in a biologically logical way. Next component, please. Okay, you can also see in this image that you may, if you don't pay attention to how you're presenting your image or how it was collected, you might see a big discrepancy in the different structures you can see. So on the left, this appears to be like a Z-stack that's been being displayed in a maximum intensity projection. So you're seeing the foreground and the background kind of artificially merged, so they look like they're in the same plane. So you might think that those structures are actually in the same physical location in Z, whereas on the right-hand side, if there was an illustration or if there was a movie there, you would see, scrolling through that movie, that the structure that you see there in the foreground are actually in a different focal plane, maybe in a different focal plane than the stuff in the background. So that can happen. Okay. And then another thing that you have to watch out for is artifacts. You can have cross-excitation and bleed-through, depending on how you set up. This often happens if you choose two dyes that are too close, and you're using either the wrong filter combination on a wide field, or you're trying to do too many channels at once on a confocal. And what you're seeing is different structures that should appear distinct, showing up, for example, at the same time in the green panel on the left there. So these are all things that you have to keep a critical eye out for to make sure that the images that you're going to analyze are actually free of these different defects. And there's also a whole other range, of like pin cushion distortion and chromatic aberrations and other aberrations that can affect your image that you also have to, spherical aberrations is a big one if you're going deep. So things like that you also have to be aware of. Okay, I think that is, I'm handing it off to, I think, Dina now.
Yep, I'm back.
Yep.
So, in the greater context of things, right? When you have a user or you yourself are sitting down at the microscope, you never just sit down and just snap an image and run away. It's part of this greater workflow. We really love having a workflow where we have users come sit down, we help them plan their experiments, we help them choose their fluorophores or microscopes. They go through, they do their preparations, then they sit at the microscope and then they image their data, and then you run your statistics. And this looks very, very, very linear, right? And of course, as imaging core facility scientists, we're most focused on imaging at the microscope and the analysis portion of it. I want to do just a little bit of a deeper touch on image analysis itself, right? When we're talking about image analysis, we have a workflow for that too, right? So each of these can be broken out. For image analysis, everybody needs to copy their data before they start analyzing it, right? It's very easy to apply your whatever changes and then you've destroyed your raw data. So copy it, tuck it off in a corner, and then work with a copied set. And then generally what you do is you apply some sort of filter, you segment, you take those regions of interest from the binary, you can create Boolean operators, but usually you extract a feature. How big, what's the intensity, etc. And then you run your stats. And this is, of course, an iterative process, right? This never works right the first time you sit down to analyze your data set. You're going through and you're running this through. So in the greater context of things, we think that this is linear. You plan your experiment, you prep it, you image, you do your analysis. But normally, it's never this linear. You sit down and you go to image and you see that, oh, my cells look terrible. Yeah, I didn't fix them right, or I used the wrong secondary, or what's going on. So there's iterations in terms of prepping your sample. There's also iterations when it comes to analysis. Sometimes you sit down and you do your analysis and you're like, oh my God, I have saturation. Hey, you know what? There's too much noise in my image. So you have to go back and image again. And sometimes you have to go all the way back to your sample preparation. And then sometimes you're actually completely wrong. You were doing this on an epifluorescent microscope. You have to go back to confocal and, oh no, I'm using the wrong antibodies, right? Sometimes you have to rework everything. So, or you run the stats and you realize that, I did this all wrong. So all of these things are iterative. We strongly advise users to start out small. Come in with your controls and then your wild type and your knockdown, your time 0 and your 24-hour time point. Can you see these differences? Can you quantify them? Can you image them? Are they clear? Before you bring in the 7 different cell lines and the 12 different time points. All right, so there's that. The other thing we want to walk through is we want to talk a little about what happens when you do things a little bit wrong, and you can make just one simple mistake, right? Like, and David's going to highlight what happens when you make a simple mistake. And we're going to do that based on just one step in this, which is segmentation, right? In the image analysis workflow, segmentation is usually the most critical part of image analysis. And what is segmentation? Well, in order to get your computer to analyze your data, you first have to help it to identify what it needs to count, all right? And most people have seen this slide. It's just these blobs. It's an image in Fiji, a sample image. And if you do just a simple segmentation, you can say, oh, look, it did a great job. I can count how many blobs are there. Well, really, maybe it did and maybe it didn't. Like, is this little spot going to count as a blob? Am I going to count this thing on the edge as a blob? Right? So there's filtering you have to do. And our brains are actually really good at filtering out things we don't care about. Right? And everybody's seen these optical illusion slides where you can't necessarily trust your eyes, even when you're looking at a simple image. If I tell you to count the gray squares, you're going to tell me I've got these squares right here that are dark gray, and I can tell you, and you can tell me which square is brighter. And in the normal world, we would say the one on the bottom is brighter. We know that this is an optical illusion, so actually they're the same shade, right? This can impact your segmentation. So I am going to pass this over to David, and he's going to talk a little bit about segmentation and thresholding and some of the errors that impact it.
So I will wrap this up, and I have only two little examples that's more leading as a teaser for the next session to say what all we talked about will influence the result. So the easiest for most of the time to do this, it's called thresholding. Thresholding means you set a value and say every under this is going to be 0, every over this is going to be the 1, the thing of I want to segment. In this case, I'll show on the left-hand side the original image. I make a small little profile out of this. This is in the center. And on the right-hand side, you can see what then will be the outcome from the binary image. So on the right-hand side, everything is white. You want to count. You can get the area of this or where this is. And you see in the center, the profile where you see that where the red is what transferred into white on the right-hand image. So when you now will saturate your image, what will happen is you will overestimate the size of the objects depending on the saturation. So in these cases, where stuff will fuse together and stuff will grow, even it's not bigger, but because you saturated this. So technically, the size of the object will correlate with the amount of saturation in the image because you will get where the border is wrong. So in this case, that's what we're saying is try to avoid oversaturation because you will screw yourself because you will overestimate the size on this. The second thing, how to easy count stuff is local maxima. They call it different programs. In Imaris, it's a spot. In Nikon, in Imaris, it's a spot. In Nikon, it's a bright spot. In Fiji, it's fine maxima. It doesn't matter. What you do is you count the amount of hills in your image. And by this, you don't care much about the background in there because you don't care when the hill is out of when a hill is a hill, it's a hill. So what you see here on the left-hand side is the original. I counted all the maximas, and then you see on the right-hand side where each maximum is. Now, when I saturate this image, there is no maximum anymore, at least not where it's popping out. So you will see when you saturate your image on the right-hand side, on the upper one is that you will undercount the events. So when you do thresholding, you overestimate the size. When you threshold in fine maxima, you will underestimate the amount of hills, the amount of objects, particles you have in your image. So try to avoid oversaturation at any cost. And we will go to this in the next session. And thank you for listening. The next lecture will be about data management and image analyzing. Most likely we will use Fiji, or Fiji is just ImageJ for this. And I guess now who takes over?
Now we do questions. So that was like a shameless plug for the ABCD series. So November's going to still be a little more theoretical. Segmentation with ImageJ in January, I think it's going to be more click-through-y.
Yeah, so the idea is to make a more like a recipe you can follow and have an idea to how to apply this in your lab.
Yeah, so I am going to stop sharing. And we're happy to take questions and
okay.
So there's a question about background versus noise.
Background versus noise.
So when the noise is low and your signal is popping out of the background, I don't care. So it just needs to be out, and when there's no noise, it's good enough. But the problem is people are saying, so I don't care when the background is high as long the noise is low and your signal is popping out, because technically you just can count maxima, meaning hills out of the background.
Yeah, so perfect example, like let's say your background has an intensity of 10. And all of the background is just an intensity of 10. There's no 9s, there's no 11s, it's just a solid 10. In theory, if your puncta had an intensity level of 11, you could still see them in those images because there'd be no noise, right? But that's never going to be the case. So there's always going to be noise. How much noise is really going to impact, how much you can see.
Yeah, I kind of think about it as the background being a kind of a non-specific level of intensity, whereas noise is more like a variation in the intensity level on the objects that you actually care about. Like if you have you might have a background level of let's say 10, like Dino is suggesting, and then maybe your object intensity is 15, but if there's noise, your object intensity might be 13 to 17, and it might vary quite a bit. So it's that kind of like that variation in signal over the object, and a lot of times it can appear as like a speckling or something like that as well, in my experience.
Yeah, and if your background instead of just being 10 is varying between 5 and 15, you can't see that, right? So it all gets mixed up all together.
And just be aware, we're talking about numbers like in the single digits, depending on the type of detector you have. Like I have one of my scopes is a Dragonfly, and it's basically camera based, and anything under 100 basically is just due to the camera, right? So you have to be really careful. Like Dina mentioned, like the silver detectors on the Olympus are really, really low noise. And even the NSpark on the Nikon, again, they're really low noise. So be really careful about what you're quantifying as signal versus, either the detector itself or, noise.
Yeah, I mean, if you're imaging in a room with the lights are on, your background and you're doing epifluorescence, your background can be in the hundreds. And it doesn't matter if your signal's at 30,000, you're totally fine. But if your signal's at 400, you're cooked. I like using this example, like if I turn on an LED, just a tiny little LED in a room with the lights off, you're gonna be able to see it, right? I'm gonna see the little light on my monitor screen. If I've got that same monitor outside in a park, you're never going to see that tiny little green light. So background can impact what you're seeing when it's overwhelming it, right? But that's not noise.
Right. And it varies tremendously from detector to detector. Like our STED microscope, you have to have the room absolutely dark. You have to turn the monitors sideways, or you can actually see the counts in there. So it really depends on the type of detector.
Our multiphotons the same way. The multiphotons behind a curtain, we have to tape over all the LEDs with black tape. Like any photon that gets in there gets picked up.
I throw a black blanket over the entire scope.
Same. Yeah, we've got it attached to the wall on a curtain, so like
Yeah.
blocks it all.
Yeah, I had the same experience with mine being behind the plexiglass blocks when we had one.
So are there any other questions?
I want to comment on one. There was a question before. They say they are fine with the gamma correction when they declare this. I get a little bit pain by this, because the reason for this is when you apply gamma, you lose the linear relationship. So there's no interpretations like when you get double, you get double the amount. So when somebody shows me an image and I don't know what the gamma is, so the actually number, I have no idea what changes in their means in the way of density. So
Right.
it's very misleading when people are doing this, because it's making me, because you can't reproduce it on this. So what happens to us is people come to us and say, okay, I have the same construct. I don't understand how they get this image because they have a high background. And then the answer is, yeah, they don't. They have the same background, but they lie to you by applying gamma or some fancy things. So everything that's not linear I would love to have at least the option to see this in the original linear scale.
So I'm with you 100%. I would love for people to dump their raw, unprocessed data. You could actually see what the original looks like. I have never seen that ever in an article, not once. Half the time you don't get gamma disclosures at all. I don't even know if I've seen a gamma disclosure, but I think at minimum it has to be in there. If you are playing with gamma, and people do this all the time, we see it in the microscopy facility where, we use Nikon, so I'm using that as an example. You've got brightness and contrast. There's a line across the middle of it, and you can just slide that line up and down. It's so easy to do. And they do it, and they screenshot it or whatever they're going to do, and they put it in their presentation. That has to be disclosed. You have to say you've done it. I do think there is a purpose for it, right? You do have dim structures. I'm tracking this particle. There's a whole glob of it in the Golgi. I can't just adjust the brightness and contrast because it's blowing everything out. Fine, I get it, but tell us you're doing it. Tell your colleagues, your peers, your scientific, community that this is what you've done, because that is the bare minimum you need to do it.
Yeah, I mean, sometimes it can be helpful as a tool to visualize what you're able to segment. If you want to adjust it to bring out certain streachers so you can see them easier, so you know that you're segmenting them properly. But it really is to adjust your gamma and not disclose it. It really kind of violates that assumption that most people are going to come to when looking at your image and assuming that there's a linear relationship between the amount of signal and the amount of a particular target that you're displaying. So when you are introducing gamma to your image, you're really violating that assumption. And so that's why it's so important to disclose it.
And you guys who review papers, I often will ask for the original data. And if they're not willing to provide it, that's a huge red flag to me. But I usually always ask for, especially like in AI papers or deconvolution or where they've done really advanced stuff, I always want to see the originals to see what they are doing.
I actually don't get asked to review. I'm not complaining about that, but I kind of am. So I'd like side mission. My side quest is I want to campaign to all journals that they change the way they are reviewing papers. I think one of the reasons we have problems with rigor and reproducibility is the complexity of papers is just off the wall, right? You see
Yeah.
a paper now and it's got flow, it's got sequencing, it's got advanced imaging, and they still are sending it to 3 people to review. And you can't. Like, I can't review the robustness of their sequencing approaches. I have no idea if that's remotely correct. What I wish they would do is pre-screen. I volunteer myself, and I'm sure half of you would too, to pre-screen a paper. It would probably take me 5 minutes if all I was reviewing was the imaging. Send me the data. I'll look at the images and tell you, yes, you have enough information here. Yes, this is valid. No, you don't. Go back before you send it out to, hey, is the biology, right within the scientific field. I really wish they would send these out for pre-review to experts in the field on the techniques. And then when you send them out to the scientific reviewers who are in the field, then they're confident that the microscopy, where they're saying they're doing super resolution, is super resolution, right? Like that at least the technology portion of it is solid. So that's the new hill I'm going to die on, is trying to get journals to implement this.
A lot of journals are doing that. I get often asked to review papers like Dina, you just described, that are super complex, and I don't have the time to spend like on the bioinformatics or the genetics. So that is definitely the way bigger journals are going. I get asked that probably 25% of the time now, is just review the imaging. Because the editors are realizing that, basically if they pick the 3 reviewers, they're only going to look at their part of the paper. And that's where, the rigor and reproducibility is really starting to falter.
And it's not a scientific integrity thing. Like, I don't,
No.
it's just impossible to actually understand the nuances of every single one of these techniques by the 3 authors on the paper. We're back in the chat, so sorry, that was an aside.
Oh.
Where are we?